But then I saw these two guys here, and I figured I'd do a little bit slightly more technical, and just a little bit about some of the experiences that I've had coming on board with a company named Agron in Fresno. So it's a little bit about scaling a team, but it's also about scaling an infrastructure and a system. So when it gets a little kind of technical, not super technical, but around, I don't know, halfway through, feel free to leave. I won't be offended or anything. There's a lot of people anyway, so. Yeah, let's get started. So just a really quick thing on Agron. So Agron is it's a company based out of Fresno. We deal with ag software. We are software as a service, so we're cloud hosted, and we solve a lot of different people's problems in agriculture kind of all over the world. From regulatory compliance, food traceability oriented things, as well as precision agriculture, which is sort of where a big data thing is happening right now, where a lot of equipment is producing a lot of sensor data and people are trying to make sense of it. We kind of check all those boxes and have a sort of unified platform in the world of a lot of point solutions. That's kind of like our big pitch. So. Yeah, so we're based out of Fresno. Actually, now I should say Clovis. We just built an office at Clovis. And we've scaled up quite a bit in the last 4 years. So this is a little bit of just some reflections on that scaling process and then some technical tidbits that may be interesting to you if you are cloud hosted and deal with database scalability issues, or we're trying to move from a monolith to a sort of a service-oriented design. We'll have a little bit of all of that. Who am I? I'm Peter Brandt. Born and raised in Fresno. I used to work with some of the people in this room at a company called Pelco. About 4 years ago, I moved to a company called Agron. There was the promise of this big picture solution of a cloud-hosted solution, and I had been working in sort of a private infrastructure world for a long time, dealing with issues of scalability in a private infrastructure world, but I really wanted to kind of take that to a cloud-hosted world. So I made the leap, and it's been a little bit crazy in a good way. I guess a little bit more about me. I'm like, I mentioned, I care about issues of scale. I'm really interested in scalability. I've donated money to highscalability.com. Just that's how much I like scalability. I gave money to a guy who has a blog related to scale. I hang out on Hacker News. You'll never figure out who I am on there. And if you do, I'm worried, but you won't. And I just finished watching American Vandal on Netflix. That's the little tidbit about me. If you haven't seen it, I recommend it. It's really weird. So now a little bit more about what Agron does, and this will provide some context for like the scalability topic. So this is going to be a lot of tapping really quick. So we have a lot of features and capabilities. You know, if you have to make like a little chart like this, you probably do a lot of weird things, right? You have a lot of services or a lot of capabilities. This is actually like only some of the things we do, but it's things that it started to get really hard to make a circle out of circles. And I didn't want to have like a bunch of just dots everywhere, so I stopped there. But, you know, I gave you a little background on what Agron does. This is probably a little bit more specific. If you were in agriculture, these things might be things that you like recognize. But even if you're not, you probably understand what weather has to do with agriculture. You probably understand what I guess planting a crop, like what crop you put in the ground is kind of important. Crop nutrition is important. But a lot of these are actually like significantly more challenging in the world of scalability than others. And I'm going to talk about 2 or 3 of them depending upon how much time we have, and kind of where we started and where we wound up. And just a little bit of background on this. I went through like our Slack history from the beginning to figure out just kind of, to remember sort of timelines of when we hit a problem and how we solved it and like what the chat history looked like. Because you kind of forget, you purge all this stuff from your brain once you get far enough along. You just think, well, let's move on to the next problem. So I went through these old chat logs, and I mean, we had scalability issues constantly, right? You have to pick the battles. There's so many fires, right? Infrastructure issues, just, you know, issues scaling actual code, not just like, you can't throw hardware at every problem, right? And yeah, it's fun to see what we chose to solve, and I think almost all the time we were right. And a lot of that was because we had data to back up the reason we tackled that issue. And it's not like it's complicated. I'm not even going to have a slide on it, but it's basically what was the source of the problem, what hurt you the most, solve that problem, let the next problem propagate, let the next problem bubble up. And in a cloud-hosted environment, it's pretty easy to have measurements of issues of scale or response time or load. All that stuff is pretty easy to capture. So I won't even go into that because you almost have to actively disable that kind of monitoring if you don't want that information nowadays. So yeah, we just picked the right things, I guess. But what I do want to talk about is some of the interesting things that happened when I came on board with Agron and how we scaled the team. It felt natural, but it really probably wasn't as natural as I like to remember it. Agron started out as one kind of just big software team. There was developers and testers kind of just in one team, and they worked on a system which back in the day, ColdFusion was the system of choice, so it was a ColdFusion system, and it was on top of like 2 or 3 MySQL databases, and if you had a problem or a performance issue, you looked at your query and you analyzed the query and made sure that it was actually using indexes or something, right? And honestly, to its credit, ColdFusion's pretty dang fast. If you're doing basic stuff, it was really fast. So they never really had that many issues, and the complexity of what they were building wasn't too great, right? It's not that it wasn't hard to come up with the idea. The ideas were awesome back then that we were coming up with, but the actual technical challenges were not huge. And a lot of that is because it was mostly form-based entry. Almost everything had a really straightforward SQL query. There was no like real ORM layer. You kind of just wrote SQL and you got what you wanted, right? It was nice. I guess you could say nice, depending upon how you see the world now. When I came on board, there was this big initiative to build what we call the next gen system. So I'll refer to like this old system as current gen and the new system as next gen. And the next gen system, kind of the basic requirements were, well, this needs to scale like crazy because we're going to do a lot of stuff and we don't know where that stuff ends. And we need the design that will accommodate adding stuff, right? Like, oh, hey, we want to build this brand new capability and it's totally new and no one knows anything about it in this company and we want you to add it in, and we want to make sure that when you build it, its code is isolated from other pieces, so that way, like, if you were to deploy it, it can scale independent of other things. And that if we want to kill it, like, we can monitor how popular it is and anything like that. So if we want to kill that product because it's not popular, we can do so without having to like untangle a big mess, right? So there were a lot of decisions like that that had been made that had no technical, like, no one had figured out how to do it technically. So we decided when I first came on that we'd go with like, the old school terminology was like an SOA, services oriented architecture. Since like 2014-ish, I think microservices became the buzzword, which is quite a bit different, really. We decided we wanted to kind of fit somewhere in between there. We wanted a separation of concerns where the boundaries of services were pretty clear, like this thing does this kind of work, and its workload is kind of specific to it. But we did want sort of like a unifying service that maybe held some truth that everybody else could refer to. And that kind of breaks the microservices model. It's not actually a real microservice design. If you do that, I don't care. I'm not trying to put on my like resume that I did microservices stuff. I want something that works for us. So we picked this sort of in between, and it worked really well. But that technical decision making right there couldn't have really worked if we didn't design a team the right way. And really what we ended up doing with the team, like day one, I think we were 15 or 16 people, and it was in 2013, around this time in 2013. When I started, we were asking ourselves questions like, because we were at the time purely Ruby on Rails, we were asking ourselves like, okay, we got this new capability, do we make it an engine? And if you're familiar with a Rails engine, it's like this mountable thing that you run with another Rails app. It's not, you don't really run it separate. So do we just build a bunch of engines and those are our services? And we tried it and it didn't work very well. We also asked ourselves questions like this. I think day one I was in a meeting that said, what is a user? Like, that's how we had no idea yet. We knew nothing at the time. We knew what a user was in current gen, but we didn't know what it would be in next gen. So to provide some context, we were brand new technology, brand new team members. I think there were 3 new team members, myself, another guy, and then a third person that I hired a couple weeks after I came on board. that were trying to introduce new technology to an existing team that had been using ColdFusion, and they were kind of chomping at the bit for new stuff. So we were like, what is a user? And you know, in the old world, they would define a schema and there'd be a database table and you got this user. But in the new world, we were using Rails, so we wanted to define a model, like proper user model. And it was exciting because there were only a handful of us that were really familiar with using that kind of design, using a framework like Rails. So that's kind of how early everything was. And it's been 4 years now, so hopefully everybody knows what a model is. And you know, I guess one of the funny questions that came up a little bit later, probably like 6 months after, we were asking ourselves, should we use a JavaScript framework and which one? Like, we were using Rails views, and you know, the single page app thing wasn't like totally that popular yet in 2013. I mean, it existed and you know, there were lots of options, but a lot of people were still thinking about having views generated from the server. And we started out that way. And then we made some decisions, which I'll go over. So let's say maybe a year in, we'd already kind of made all the decisions. So we're like, yeah, we're going to have services. So each service is going to be a Ruby on Rails service with likely a Postgres database. And if we need caching, we will use Redis. And it's cool. So Postgres, Rails, Redis, and then the UI we picked was Ember.js for our JavaScript framework. And I guess at that point we kind of had a good path forward. We knew what we wanted to do. There weren't going to be any more holy wars about technology selection. It was like we can move forward and everyone can be comfortable. We added a couple things along the way, like a message queue that really helped us. The design was such that every single service needed to know about this hierarchy of resources that everything relates to, and that hierarchy of resources is stored in one service, so changes to that hierarchy impacted every other service. Message queue came about, we selected RabbitMQ. Everybody will tell you use Kafka or use some other message queue. Rabbit's been amazing and I don't have any complaints. So we selected Rabbit early on and we've stuck with that. And then we also selected for our cloud infrastructure AWS, not Google, but at the time there really wasn't, Google didn't really have something yet. And we're slowly moving actually now to a more sort of provider agnostic solution using Terraform and things. So maybe someday we'll get Google as our backend. But so we picked AWS, we had this front end framework, we knew what our services would look like. We knew how our services should talk and what their responsibility boundaries should be. We were kind of ready to go. And I think after that first year, we were just starting to really, really pick up pace. And that's when we built like 8 services in like a year. And they're not small, like they're not microservices like get some data and do something with it and return it. They're like full-on features that somebody might sign up to pay to use exclusively and run their business on. So there's like a ton of these. And I think that early selection of those technologies really helped us. But once we selected all these technologies and started building all these services, we needed to have teams that could support those services. And with all this new technology, we kind of didn't really know who's a lead, right? What is a lead when everybody's kind of like at ground zero, like as far as their familiarity with this tech stack. So we managed to figure out who wanted to be a lead. A lot of people don't want to be leads, and I think that's healthy. We got the right leads, I think, in place. And we started out with, I think, 5 teams, and the design was what we call service lead design. So each service has a lead, and that lead is in charge of it from top to bottom. They're in charge of the API documentation, they're in charge of the repo, the deployment strategy, the DevOps, everything. And some team leads had more than one service because maybe some of the services they were managing were a little smaller than others. But we decided, okay, no more monolithic team. We're not on a monolithic giant ColdFusion app anymore. So why don't we make the team sort of model after the technology? And if you look on the internet, you read a bunch of people's stories or retrospectives of like failed startups, people will tell you that you don't want to do that. You don't want to model your team after your technology. You want to model your team after the business needs. What's kind of interesting is our technology and business needs were kind of like one and the same, because the technology we were building was often kind of regional, and the business needs of each region would necessitate this technology. So we kind of just lucked out. It could have really hurt us in the long run, But it worked out that the business needs and the technology were sort of one and the same. So the teams understood the business needs pretty well, and they got to build the services. So that's kind of what we ended up with, was this service leads design. And I think now, I wrote it down in my notebook, but it's like, I think we have 9 or 10 teams, and I think we have 13 services or 14 services. So there's obviously many people that have more than one service, and some services are bigger than others, but it's actually served us pretty well. And as long as you have leads that want to collaborate and are open-minded, you know, it works pretty well. So we decided to do service teams. We found out that not all of our services are the same size. I mentioned some of our leads wound up with like 3 or 4 services, right? And it actually worked out okay. You know, if it's a small service, you can handle 2 or 3 of them, right? It's just code and you're deploying it. And we do deployments on a fixed interval. So our leads, if you had to deploy, you know, 3 services, you just run deploys on 3 services and it's automatic. It's not that tricky. But early on, when we first started thinking about this service lead model, we didn't know that services would not be of a fixed size. So we thought, oh, I'm going to have to hire a lead for every service. And we know in the long run there's going to be like 15 of these. I don't want to have 15 leads. That's going to be crazy. And some of them are so tiny. Like we have this, I don't know, we have a service that does zone making. Zone making is probably way too complicated for this talk, but it's actually not that complicated in code. And I don't want to have to hire one person to manage something that gets changes very infrequently. So I don't know, I guess what I'm getting at is those kind of rules that you create, those arbitrary rules before you scale a team where you say, you know, 1 lead per service, that's how I'm going to budget. It's probably not wise. I mean, I thought that way and I realized later that's not going to work. And we started cramming them together and putting the right number of services of the right size for the right person, the right lead. So yeah, we just had to keep that in mind. And going back a little bit on the service teams, obviously the other risk of having service teams where the technology and the business needs and all that stuff is kind of combined and you have a lead that's in charge of that is that you could get, you know, some pretty substantial siloing occurring. I'll go into that a little bit toward the end, but generally speaking, I think you're going to have silos. And I think it's up to you and your team to break them down with communication across teams. And you can have like team sabbaticals. Like we've sent people from one team to another for a while, and it's been really, really helpful. I think where it becomes very difficult is if you have substantially different technology in each team. So if you like have one team that's doing Rails, and you have another team that's doing Django, and you have another team that's doing some framework of the month, that starts to become really hard, and the churn is really difficult. And people don't like learning a new framework every month. So that's why picking Rails was pretty wise. Or maybe not Rails, but picking a framework was pretty wise. So now I'll talk about scaling the system a little bit more detail, and then I'll kind of tie it all together. But scaling the system, I picked a couple examples that we ran into during the course of these 4 years. Not really like groundbreaking, but there's some interesting anecdotes here. So I mentioned that we did not go the microservices path. And I promised I'd invoke Martin Fowler. This is Martin Fowler's, I believe it is Microservice Premium. You can find that blog post on his site and read it and feel like you're dumb afterward because he's super smart. Basically, early on, we asked ourselves, and we continue to, I think every time we get really pissed off because something doesn't work exactly the way we want, we ask ourselves, why did we do this service design? It would be so easy if everything was in the same DB. Can you imagine? The reason we didn't do it was because our system is sufficiently complex. If it was a simple system like the current generation system was, where like there were generally maybe 10 things that were a little different that the system could do, but not like such variability to where like the workload was so substantially different. We had so many different usage patterns and so much different workload that we kind of fall into this category where we actually do need something that's more like a microservice. So if you look here for like simpler systems, there's a lot of baggage required to manage microservices. Like the deployment story is more challenging. Just having a bunch of different repos can be a little bit difficult in and of itself. having those different teams like I described, there's overhead in that. And in general, you've basically created silos potentially. If you have like one giant system, everybody's in the code, everybody sees everything, they kind of generally understand it, hopefully. But if your system is sufficiently complex, right, you start to get to this point where your productivity with a microservice gets a little bit higher, and your monolith can't really keep up. So anyway, that's really all that Martin Fowler is saying here, and I like to pretend like we thought of this early on, but we really didn't. It just kind of worked out. But I think we did think a lot about things like this at the time, and it really did help us out. Anyway, Martin Fowler is super cool if you haven't read his blog. So I've been kind of referencing this a little bit, but we needed to have different homes for different workloads. So we had different databases, frameworks, languages, infrastructure, scalability requirements, consistency expectations, and just general cost sensitivities for each service. It's like completely all over the place, right? We had that circle of all those different features or capabilities. Each one of those is different, really. I mean, yeah, we have a lot of Postgres databases, but we use them differently. Yeah, we have a lot of Rails apps, but we also have Scala apps. Yeah, we have, infrastructure on AWS, but we use like 20 different, EC2 instance types. And each one of those comes with different scalability characteristics. And with each of these different DBs, you have different consistency parameters. With Postgres, we have good consistency. With Elasticsearch, not so much. And cost tolerance is all tied into that as well. So there were like tons of considerations that we had to make while we were scaling up from the infrastructure and the technical side. And I guess some of the examples I'm going to give here are like instances where we learned that we needed to have a different home because of these different workloads. And I'll give some examples of how those workloads, basically how we got stuff to scale that wouldn't otherwise scale easily. Sorry, I have two presentations open because I'm using a Google Chrome and I can't see my presenter notes. So if I'm on the wrong slide, just tell me. I'm switching two slide decks at once. Postgres scaling. So this was kind of really fun. I mean, super stressful, but really fun. So I mentioned we picked Postgres as sort of our standard database. Well, if we go back up here, oops, let's go way up here. So we have this service called Logged Data and Wireless Data Transfer. So that is a service which, when a combine or a harvester or a piece of like actual like ag equipment goes over a field and takes crop off the ground, like it's harvesting corn or wheat or soybean or whatever it is, most modern harvesters have what are called controllers. Basically all that is it's a visualization of how much you're harvesting at the time and all these other parameters. Because this equipment has like tons of sensors now. And that data is super valuable for growers because they can do a lot of stuff with it and we can do a lot of cool analysis with it. The challenge is that over the last like 15 years, the frequency that those sensors sample at has gotten to be insanely tight. Like you get easily 10 samples a second from some of these sensors, and when you've harvested a 200 or 1,000 acre field like you get in Canada, that is a ton of data. And I don't think we really predicted very well that sample rate would go as crazy as it did. We didn't really know what was in the works at the time. We didn't have friends at equipment companies yet. So we were surprised. And let me go back to my slide. So what we found with that log data system was in the first year we had a lot of users putting their log data into our system. They just uploaded it manually. They put their thumb drive in the controller, copied the file over to their thumb drive, went to their laptop, uploaded these big files, which sometimes are gigabytes. And we had some challenges even getting that to upload correctly from a browser, which that's another story, another day. But once we got that data sent to us, there could easily be 100,000 data points in that file. And we needed to put it somewhere because we wanted to do cool stuff with it. So we put it in Postgres. Postgres has geospatial extensions. All this data is basically time and space and a value. Great, we'll put it in Postgres. Well, we didn't really realize how popular the feature would be. And I mentioned we didn't know how these sensors would evolve. And we ended up like in the first year kind of hitting a wall with 100 million rows of this data because Amazon's RDS Postgres instances of the time, you could provision IOPS so you could get like more disk throughput. We basically hit a wall. We hit the limit. We could have gone to like this crazy tier that was like a big leapfrog tier in performance that would have been insanely expensive. We decided, okay, let's just stick with what's tolerable and we'll tweak the database as much as we can. Didn't really work. And we were in the middle of harvest season and we had more data coming in all the time. So I had all these crazy ideas of how to make it better, but nothing would be easy. So what do? We threw money at it in hardware. And we took it out of Amazon and we put it in a co-location facility in Fremont and built this incredible, PCIe data center grade SSD server that was insane and whatever. And it scaled, but we get to like 300 million rows and the same problem. We were still in the same boat. And it's like, what are we doing wrong here? And I don't know if it was common knowledge at the time, but like back then, nobody was really getting much above billions of rows of this kind of data in Postgres. There was no evidence of it. I'm sure it was happening, but it was probably at really big shops. So we decided to all pick up books on Postgres and read and prototype as much as we could and just seed data into local Postgres instances and just try different things. And in a past life at Pelco, I had done some Postgres scaling, but most of it was like at the operating system level and a hardware level. And it was really helpful for what I was trying to do then, but the data was so different, there were no parallels. So I picked up this book and I learned about what's called table partitioning. And it's really common now in databases to do table partitioning. Back then it wasn't. And in fact, Postgres 10 automatically will partition your tables for you so you can hit like great scale with Postgres. But back then it wasn't. So we decided, okay, let's experiment with this. Our data is time and space, temporal spatio data, right? We could, if we wanted, we could say, I want to create a table partition, which is like a subtable, if you will. It's like a chunk of a table that you can query discretely. We can create like our key to partition our table spatially. So we could say like, we'll cut up the world into a bunch of chunks, like squares, right? And every time data gets written into one of these squares, we'll make a new table partition. Started thinking about it. We decided we would use the UTM Grid System, which is one of the common grid systems for the globe. And we figured out like where all the data is coming from is like the Midwest. I mean, that's where everybody has these harvesters. And so I'm going to be cutting up the Midwest to small chunks, and then in the rest of the world, I'm going to be cutting to bigger chunks. And now I have this problem where I have hot partitions, right? Some are like super frequently queried, and others are like never queried. They could be almost empty, right? Okay, well, let's think about time. Time started to make a little bit more sense if we partition on time because, for one, the way that we were logically grouping these data points was by time. So we would say, okay, we think this is what we call an event. The harvester started at this time and it seemed to end at this time, and we can group that together and then summarize it and make it visible to the user, and this is your harvest event. So we used time for that. Started to make more sense to use time. We prototyped it a little bit. We decided to table partition by, I don't know if it was hour maybe. I think it was hour, or it might have been day. I think we started with day and we moved to hour. But that was amazing. I mean, there are times where there's no data, like in certain times of year, there's nobody harvesting, right? I mean, maybe on the equator if you're harvesting sugarcane, but you probably don't send your data, you don't harvest your data with the same kind of equipment anyway. So we found like, great, so now we have like the South America time of year and we have the North America time of year, and we have now thousands of tables, but Postgres doesn't seem to care. And now I can like create an event, right? I can say I want data that belongs to this machine that occurred in this span of time, and now I'm only hitting a few of these table partitions instead of querying this ginormous table that just falls to its knees. So that turned out to be super helpful. We basically never worried about scalability on Postgres again, and we hit over 20 billion rows in Postgres, which I still have yet to find someone publicly saying that they've stored that much geospatial data in one Postgres database. And once again, I guarantee someone is, but I'm publicly saying that that's what we hit. And then, so because of like this experience, we're like, okay, great. We can store anything in Postgres, and we can scale table partitioning. And most of our services are 100 million, 200 million rows, maybe half a billion. But we had this other one that we were going to be building, and it was a satellite imagery service. And this is where we get satellite imagery from all these different providers. And if you think about the amount of ag land in North America alone, it's like if you just zoom in on a map, you can like zoom in anywhere that's not a desert, and even in deserts, there's tons of ag land. Well, we were going to get all this satellite imagery so we could help growers understand how their field is progressing throughout the season, and get all this extra information in the non-visible light spectrum that tells you about plant health and all this fun stuff. We're like super excited. Problem is, we wanted to put it in Postgres because you can technically store rasters in Postgres, but we were going to run into that same problem again. How do we cut up this data in a way that makes it queryable and scalable? So we decide, okay, we could do it in two ways. We can do it in time or we can do it in space, right? Well, it turned out we did it in both ways. We cut up the data into squares that were like 50 by 50 pixels or 256 by 256 pixels. We kind of waffled. So each row was raster data encoded in that square in this place in the world. And then it also, so the rows were cut up that way, and then the table was cut up in time again. Same thing we did with that log data. And I can't even tell you how many, I actually tried to query the database earlier to figure out how many rows are in that one, but it was a number that's even bigger than that other number. And it was really cool. I mean, it worked great. What didn't work great is when you needed to do a database migration that affected everything, but another story as well. So we had this pattern that seemed to work really well with Postgres. We were able to scale when we had these types of services, right, that were unique, right? The whole kind of different homes for different workloads. Like it could be the same DB but configured completely differently. So in this case with Postgres, table partitioning. Then we decided in the last, I don't know, maybe, when did you start?
2 years ago.
2 years, so about 2 years ago, probably around the same time you started. We decided, okay, some of this data just does not, we don't need to query at all, right? I don't need to say like, I want to select 50 table partitions and make some query. And certainly don't need to do that in real time. I need to look at like, event level data, right? That's kind of constrained in time and space. So we started talking about moving to OutDB, and OutDB is, I don't know if it's a common term, but the PostGIS guys use it a lot. And basically what it means is you have some kind of lightweight piece of data stored in a database that is a pointer to data that's not stored in the database. It's stored on disk somewhere. And you're probably all familiar with, like, I think Google has like an object storage system. Amazon has S3.
Data store.
Is that what it's called, data store? So you can basically write as much as you want to it and read as much as you want to it. And there's like scalability isn't a question. You have like, yeah, you have perfect, like the latency is always a known quantity. The transfer is generally consistent, the transfer speed. And it's really kind of awesome. It doesn't perform as well as having like a big array of SSDs, but you can work with something if you know what it's going to perform like. You can accommodate a fixed level of performance. So what we decided to start doing is, well, shoot, we have spatial information. We have time information. Let's just only index those characters, like very lightly index those attributes, and then we'll store blobs of information on S3. And then if I need to get out more data, I'm going to query the database and find whatever I care about, and I'll probably greedily get too much from S3, but it's so fast. Who cares? I'll just throw the rest of the data away that I don't need for that query. So we kind of moved to that model, and it's been awesome. Like storing data in Postgres, terabytes of data in Postgres, like in one case 100 terabytes in one Postgres instance, or maybe it's 90 terabytes. That is really expensive. On Amazon, you would use GP2 SSD. I mean, we're talking like $20,000 a month, right? On S3, it's like, I mean, it's like nothing. I mean, it's hundreds of dollars maybe. So we moved to OutDB, and it's just changed the way we see the world. It's enabled us to do so many things. We can do really, well, here's some examples. I'll actually read my notes. So a good example was the satellite imagery. It's probably unlikely that I need to read 1 pixel of data, right? I need the pixel here, just this one, and I want that data. Funnily enough, with the OutDB design, we can handle that. It's the same scenario. You get the whole blob, like you get 400K of information, and you throw away 99.99% of it, and you get the one thing you need. But 400K is nothing to transfer to a server. And you get all that, whatever, 11 nines of durability on S3. That's better than I'll ever get with a database that I'm managing. So it turned out to be really amazing. We can do really fun stuff. We use Spark for some analytics stuff in the back end. And with Spark, if I have data that's cut into fixed sizes and I know what data I want to grab, I can parallelize, essentially map reduce over that data and get an answer. If I did that on the database, I'd just break the database, right? I can't read that much data simultaneously off of Postgres without making it unhappy. I can read as much as I want from S3 and no one even cares. I just get a slightly higher bill for making that many API calls. So moving to that OutDB enabled Agron to do lots of crazy stuff. I guess this was kind of by design. We knew we could do analysis that way, but it's helped us like incredibly. And we still use Postgres. We still store those pointers to the data in S3 in Postgres. We just get to make fewer queries now, and we actually started using Elasticsearch as well for some of that. So we started to differentiate like each service's needs a little bit to where if we know we want to get 1 million pointers to the data, we're probably not going to do that against Postgres. Instead, we'll make 10,000 requests, and we'll aggregate those pointers to the data, and we'll say, well, what was 400 kilobytes is now 10 megs, right? We just kind of expand it, make fewer things to make better scalability, because network throughput is pretty amazing these days. So some just kind of final thoughts. Well, let me go here first. So I don't think a monolith is a bad thing. It's not a dirty word. I think it's really actually important, especially in most startups world. Like you have this much money, like you have so much money, right? You can't run like 150 servers, right? You probably want to start small. But if you build with a monolith early, knowing how you can break it up later, things can work out for you. As you scale, you can actually separate the pieces and run each piece separate from one another. So you're always kind of having to keep track of what the workload of each piece is, and as long as you know what the pieces are, you can manage that workload. So I definitely don't think a monolith is a bad thing. And as Martin Fowler said, wherever a monolith is less complex than a services-oriented design, you should probably use it anyway. Saves you money and time and pain. Some other thoughts about the team. Wait a second. So, knowing Conway's Law, everything I've just talked about is generally related to Conway's Law. We structured our team in a way that we modeled the team after the technology, right? Which just happened to work with the business needs. Conway will say, organizations that design systems are constrained to produce designs which are copies of that organization's communication structures. So if you have like a team that's already set up first, and then you want to go build your software, you end up with a software that sort of looks like your team. And I guess kind of using that monolith idea, if you're trying not to build a monolith, but you have a monolithic team, you're probably going to end up with something that resembles a monolith anyway. So I think we were kind of lucky in that we allowed the technology decisions, our aspirations, our technical aspirations to affect how we modeled the team. And I think that only really happened because much of the last 4 years was kind of an experiment. We were like, none of us had ever scaled a team this much. None of us had ever scaled infrastructure this much. We had to rely on what had worked, what we could research and learn and talk to our friends that did startups and had worked at other companies. And this Conway's Law was referenced many times and kind of helped us. And that's it. Conway's Law. Martin Fowler. Done. I have a spare slide. Any questions? I'm sure I covered everything, so there shouldn't be any.
What are you doing about like integration of the services?
Like external third parties?
No, just among the services that are coming up.
Yeah. That's a good question. So early on, we were all Rails, right? So we built some Rails gems, Ruby gems that were kind of, I'm sure Cole hates them, but we have one called Agron Action, And it lets one service talk to another service in a way that's like abstracted and easier. So it can understand what's inside that foreign service a little bit better. Totally breaks some general principles in service-oriented architectures, but it's been amazing. Doesn't work so well when we introduced some of our Scala apps. But I think what needs to be known by every service about other services is pretty straightforward. It's this core service which has these resources that are hierarchically organized that other things relate to. And as long as you can untangle that hierarchy, you know as much as you need to know about the world. So services like Agron Action enable other services to get to reference data and understand foreign IDs and things. But generally, you just make a RESTful request and you can resolve anything anyway. So you could either use the documented API or sort of internal API, or you can use this gem that's just makes the API easier. That's generally how we do integration between the services. Also, I mentioned the message queue. Changes to those sort of primary resources in the core service are always announced on the message queue. And as long as you have a listener, you can update your view of the world related to those things. So those are kind of how we do integration. So we don't really deal with service discovery at a platform level very well, or really at all. We do kind of, within each service, there's some amount of understanding of service discovery. We have, is it about it? Is that the thing? Basically, the Rails guys can know about other services by revving this, is it a YAML file or something, or some sort of configuration, but it's not automated. In the Scala world, we use, what is that thing called? We use this, whatever, HashiCorp thing, Consul, C-O-N-S-U-L, for service discovery, and it's been really great, but we haven't gotten everybody else on board yet. Eventually we will. It hasn't been a huge problem because a lot of our Rails services don't require auto-scaling, so there isn't like new stuff coming on and off a lot, so you can pretty easily rev that service discovery sort of gem. But in the Scala world, like last night I ran 300 instances, right? And then now there's like 20 running. So there does need to be some amount of service discovery, and we use Consul. What do you use, Rippy?
Internal.
Oh, like private. Oh, you do? Yeah.
That they register with.
Nice. ELBs?
Yeah.
Nice. Yeah, I will say our like DevOps game is decent for like security and things like that, but it's not great for like taking advantage of really, I shouldn't even call them advanced, but like unnecessary but awesome AWS capabilities. We just aren't there yet. That's what I was going to close with. We're looking for like DevOps people, so if you know AWS. But yeah. Any other questions? BigQuery?
Yeah.
I have, yeah. I really think it's super cool, and it probably would benefit us for some of our workloads.
The right kind of data.
Exactly.
I've tried it.
A lot of our data that like we need to look at through like a sort of an aggregate lens, we put into Elasticsearch, and we can do pretty powerful querying. We've experimented with Accumulo, which is another big table designed columnar data store, which I really like, but it's sort of a pain in the butt to maintain. BigQuery is really cool. I think the latency requirements might, in some cases, not be met by BigQuery for us, but for, like, if I have a customer that has, millions of things in our system that they want to do something interesting with, like they want to pay us to just give them access to Bigtable, that's been something we've talked about. And it is pretty fast. I mean, I was just complaining about the latency requirements, but it is pretty fast.
Your applications are large, your data, is it stored in a multi-tenancy model, or do you have like certain clients' data siloed because they're so huge? Or?
So in database, we do logical segmentation. So we use like a nested set design. So everything, like I was talking about those associations, every single thing that's ownable or like associable has those attributes of like those primary resources that they're related to. So if you're querying for something, you can't get to anybody else's stuff because you're forced through a filter that checks on those associations. As far as S3, yeah, it's like, S3 is nice. You can do that really easily. But But we do not do, like, we don't have separate cloud deploys for different customers or anything like that. We talked about it a lot early on, but I think we realized, like, with meeting our customers, there's already, generally people are okay with being in a shared, you know, a shared infrastructure design, because that's what everything kind of ends up being nowadays. So when I meet with a CIO at a company, the conversation doesn't even come up now. Luckily, because I don't want to separate our system into a multi-tenancy model. Any other questions? Stephanie? Not now?
Not yet.
No? All right. Cool. Well, thank you.